Measured. Look at this structure. It represents the last decade of global edtech. The industry successfully achieved massive reach and scaled access to information. But despite reaching millions of users globally, the actual learning outcomes remain highly inconsistent. The primary symptom of this paradox is obvious: massive enrollment numbers paired with drastically low completion rates. Learners are perfectly capable of consuming video content. The breakdown occurs because they structurally struggle to translate that passive viewing into practical action. Modern professionals are no longer seeking knowledge simply to possess facts. They enroll to solve specific workplace challenges. Sitting through a generic lecture provides no immediate utility for someone needing to execute a complex career transition or deliver an urgent business outcome. Direct. Existing platforms have engineered the scaling of content delivery while leaving the problem of contextual application to the individual learner. This diagram shows the required architectural shift. Left, the legacy course-first system forces learners into pre-packaged content, creating a massive bottleneck on a single track. Right, the problem-first model. The learner defines their real-world problem, which automatically generates a custom learning pathway. Resolving the edtech paradox requires utilizing AI to dynamically map modular content around that specific user objective. This engineering approach generates a scalable, outcome-driven AI learning playbook designed to facilitate a specific, predetermined result. This linear flowchart shows the rigid parameters of the traditional course-first model. The system relies on fixed pricing models and inflexible progression tracks. The variable that breaks this architecture is the contextual divergence between two learners taking the exact same course. These two theoretical learners bring entirely different inputs: disparate end goals, baseline experience levels, and unique time constraints. One learner might be seeking a complete career transition into a new industry, while the other simply needs to solve a localized business challenge by Friday. Despite these vastly different inputs, the platform delivers the exact same static output. Giving identical learning experiences to diverse profiles guarantees a structural gap. The primary bottleneck of legacy edtech is treating highly individual human contexts as identical, generic data points. The new architecture requires a different trigger mechanism. Rather than selecting a course catalog, the user onboards by inputting a specific, real-world objective. This diagram maps the user onboarding process for an AI product management case study. These spinning parameters lock to create learning DNA, the foundational personalization layer for the AI system. In the first phase of extraction, the system evaluates current role experience against specific future goals. Next, it plots strict time constraints against existing skill strengths. Because of this deep variable tracking, two learners pursuing the exact same goal will register completely different learning DNA profiles. This prevents the systemic error of generic segmentation. Successfully mapping learning DNA is the mandatory engineering prerequisite for generating a tailored learning environment at scale. This web-like database is the playbook generation engine. The AI evaluates the user's learning DNA, searches this database, and dynamically pulls only the necessary micromodules required to bridge their specific skill gap. For our AI product management case study, the initial stages of the assembled playbook feature Level 1, AI Foundations, and Level 2, Product Thinking. The advanced stages cover Level 3, AI Product Strategy, and Level 4, Real Project Application. These assembled modules are highly interactive tasks, integrating constant AI coaching, using both text and voice, to guide the user through decision-based scenarios. This architecture forces learners to make choices and apply knowledge immediately. This continuous requirement to solve microproblems forces the learner from observation to functional expertise. This diagram illustrates the transition boundary between Level 2 and Level 3. Deeper playbook levels remain completely inaccessible until specific outcome milestones are met, like completing a real-world action step. This mechanism guarantees incremental value creation for the user at every stage, rather than backloading all the value at graduation. It removes the option to skip ahead. ROI-driven progression ensures the learning experience remains perfectly aligned with verifiable, real-world capability development. This split screen compares the final outputs of both systems. The legacy pipeline on the left generates learners who possess raw data but lack practical direction or application skills. The dynamic pathways on the right output professionals who have actively resolved their initial career transitions or business challenges during the learning process itself. The designer's challenge is now the dynamic mapping of modular content to a unique human problem. By focusing the AI on specific user objectives, the platform serves as a navigator through a complex, personalized skill acquisition journey. This is now achieved through 3 core engineering mechanics: deep micro-personalization at scale, interactive playbooks, and ROI-based progression. Problem-First AI Learning Playbooks establish a system where online education yields measurable, real-world capability development.